This video is about section or activity 4.4, and it's called The Amazing Property of Gravity. In the 16th century, scientists such as Galileo were experimenting with the physical laws of gravity. In a remarkable discovery, they learned that if the effects of air resistance are neglected, any two objects dropped from a height above the Earth will fall at exactly the same speed. That is, if you drop a feather and a brick down a tube whose air has been removed, the feather and brick will fall at the same speed. Surprisingly, the function that describes the distance fallen by such an object in terms of elapsed time is a very simple one. S equals 16t squared, where t represents the number of seconds elapsed and s represents the distance in feet the object has fallen. The algebraic rule, s equals 16t squared, indicates the sequence of two mathematical operations. You start with a value for input t, you square the value, then you multiply by 16, and this will give you the output s. So we want to use this algebraic rule to complete this table. So if t is equal to 0, then 0 squared is 0, multiply that by 16 and you get 0. 1 squared is 1, multiply that by 16, you get 16. 2 squared is 4, and 4 times 16, well, 64, but we'll just do that on our calculators to make sure. 4 times 16 is 64. And then if you square 3, you get 9, and 16 times 9 gives you 144, I believe. How many feet does the object fall 1 second after being dropped? So we would go to the table and look at that, and after 1 second it has dropped 16 feet. 2 seconds after being dropped, it's fallen 64 feet. Determine the average rate of change of distance fallen from time t equals 0 to t equals 1. So remember, the average rate of change formula is the difference of the y's, y2 minus y1, over x2 minus x1. And so we want to take 64 minus 16 on the top. And on the bottom, we're going to have, oops, sorry, did that the wrong way. Let me change this. We wanted to go from t equals 0 to t equals 1. So 16 minus 0 on the top, and 1 minus 0 on the bottom. And so we get 16 over 1, which is 16. And this is feet per second. And what are the units of measure on the average rate of change? We already have that. That's feet per second. So I've written it a little bit differently. Here I wrote the word per out, and here I wrote it as division, but they mean exactly the same thing. Explain what the average rate of change indicates about the fallen object. So what this means is that each second, well, and it's the average rate of change. So on average, the object will fall 16 feet every second. Between 0 and 1 second. Now we want to determine and interpret the average rate of change of the distance fallen from time t equals 1 to t equals 2. And so again, average rate of change is going to be y2 minus y1 over x2 minus x1. And we want to do this now from t equals 1 to 2. So that was what I was doing before. So 64 minus 16 on the top. And 2 minus 1 on the bottom. So if we take 64 and subtract from that 16, we get 48. And that would be over 1, so it's going to be 48, and that's feet per second. And so what this means is that on average, the object will fall 48 feet every second between 1 and 2 seconds. Is the function s equals 16t squared a linear function? The answer is no. And the reason that I know that this is not a linear function is because I had two different average rates of change. So the average rate of change is not always the same. In order for something to be a linear function, the average rate of change would always have to be the same no matter what two data points you choose to calculate the average rate of change. If the object hits the ground after 5 seconds, determine the practical domain of the distance function. And so the practical domain would be from 0 to 5. And so we're going to write that as an interval. And I'm using square brackets because we would be including 0 and we would also be including the 5 seconds. On the following grid, sketch a curve representing the distance function over its practical domain. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So every other will be 1 second. We're going to assume that it hits the ground after 5 seconds. So our first data point was 0, 0. And then we had 116, and we need to label our y-axis. Our x-axis is t, and this is in seconds. Well, wait a minute, let me see, how did they write that function? S and t. And so this is s, and this is in feet. So this is our distance. And I just want to calculate the distance when t is 5, because we haven't done that yet. And that's where our top range needs to be. And so that's going to be 16 times 5, or 16 times 25, excuse me. And we get 400. And we have 1, 2, 3, 4, 5, 6, 7 tick marks here. So take 400, divide it by 7, and see what we get. And we get 57. So we need to use at least 57, if not something bigger. And I just want to go to my table of values. So they're all kind of weird values. So let's see, what would be a good, so maybe 75 for each, so every other would be 150. Or we could go up by 50. That would be, at least then our top number will match nicely. So why don't we just do that? Okay, so the data points that we have 0, 0, which we already have on there, and then 116. And each of these are 50. So there's 50, and then so half of 50 is 25, so we're going to be about a quarter of the way up, a little over a quarter of the way up. And then we have 264. So 50 is right there, so again, just above that point. So that was 116, and this is 264. And then we're going to start going up pretty fast here. We have the point 3, 144. So that's almost 150. And then the last one is 5, 400. And then you can connect these dots with a smooth curve. And then we want to verify this on our graphing calculator. So let's see if I can get my graphing calculator to work today. So we already have our viewing window. We want the x's to range from 0 to 5, and the y's to go from 0 to 400. So if I want to enter in some equation into my graphing calculator, I hit this button right here that says y equals. So if I tap that, now we'll have this screen up, and we can type in our function. So our function was 16, and then times, and then we want x squared. And the way to get a variable up is to push this button right here. It says xt, and that's a theta. It's for when you're using angles, and then n. So if I hit that, an x will pop up. And then to square something, I do have an x squared key on here, or you could hit the caret symbol and a 2. So either way is fine. So I'm just going to use my squared key. And so now I have 16 times x squared in my calculator. Now I want to set my window. So if I hit graph, it has a preset in there, or if you've changed it, it'll be whatever you had in there before. So see, this doesn't look like the graph that we have. I want to make it look like the graph that we have. So I'm going to click this window button right here, and this will allow me to set my tick marks on the graph that I see. So right now, this x min is the smallest x value that shows up in your window. X max is the largest x. X scale is how many what spacing do you want to have between tick marks. Y min is the smallest y value. Y max is the largest y value. Y SCL is y scale. So how many spaces do you want, or how many numbers do you want between tick marks? And then this x res you can just leave at 1 all the time. So I want to change my x min to 0, so I can just type in a 0 and it will just replace what was there. And then hit the arrow down key, and that'll bring me down to x max, and I want to change my x max to 5. And then arrow down again. You can leave the x scale at 1, or if you want it to match our graph exactly, then you would change that to 0.5 because that's what we have. And then our y min, hit the arrow down key again, and then we want our y min to be 0. That's what ours was on our graph. And then arrow down again, and our y max was 400. So change that to 400. And because there's such a big spacing between 0 and 400, you want to change this y scale. Because this would give us 400 little tick marks, and that's just going to be too many. So I would say that 50 would be a good y scale for that, or 25 would be okay as well. So now I have all of those changed. And now if I hit this graph key, it'll bring up the graph, and it should look very similar to the one that we graphed. And so here you can see that our graph looks just like the one that that's on our window right now. So that's how you use your graphing calculator to graph a function. And so now, does the point 2.5, 100 lie on the graph? And what do the coordinates of this point indicate about the falling object? So you can check that by plugging 2.5 in for t. So that would be 16 times 2.5 squared. And we can do that calculation. So I would do 2.5 and then square it. And then hit times 16. And we get 100. So when we put 2.5 in, we do in fact get 100. And so what this means is that at 2.5 seconds, the object has fallen 100 feet. Does the point 4.5, 324 lie on the graph? And so now I'll do it the other way. We could go over to our graphing calculator, and we could use the trace function. And the trace function will put a dot on your graph. And so you see right now it's actually on the point that I was interested in, 2.5, 100. But now I want to know about this other point, 4.5, is it 324? Well, we can arrow over to the right and it'll move the little cursor, and you want to move it until the x value that shows up here is 4.5. So hopefully it'll land right on 4.5 evenly. And it's pretty close, but not exact. It's a little bit above, and if I go down, it doesn't match exactly either. But so you can't really tell exactly there. We could go to a table of values, and we can set our table values also. So see, there's a word table right here in blue. So if you switch over to the table, so now that's what's coming up in my window here. So right now it's going up by 1. So we can change how that's going up. And so for that you want to go to table set. So hit the blue key and window. We'll bring you to the table setup. And so our table is starting at 0, which is fine. And then this triangle, remember, in math means change. So change table 1 means it's going up by 1 each time. So arrow down until you get to that, and if we have it go up by 0.5, then 4.5 will show up in our table. And so then now we can go back to our table, hit the second key and the graph button, because that's where table is. And it'll bring up this table, and now 4.5 is in there, and we can see that the y value would be 3.24. So if you have a graphing calculator, you can do some of these things without actually doing the calculations. If you don't have a graphing calculator, you can still just plug 4.5 in like we did with the 2.5. So we would want to square 4.5 and then multiply by 16, and we'll get the 324. And these are both feet, and we should label those. And so the answer is yes, and the answer was yes here as well. I didn't actually answer the question. What do the coordinates of this point mean about the fallen object? And it means that at 4.5 seconds, the object has fallen. (324 feet). Use the graph to estimate the amount of time it takes the object to fall 256 feet. So we would want to go to 256, which is on the y-axis. So that's going to be right above 250 here. And this is just going to be an estimate. It's not going to be exact. And you would go from that point over until you hit our graph, and then you would go down. And so remember, each of these tick marks is a half, and so that's not, it's about a quarter of the way up. So half of that would be 0.25, so that's what? 4.3 maybe or something? No, yeah, about 4.3. So if you want to do this algebraically, this 256 is the s value. And we want to do that algebraically right here anyways. So this is our distance, which is s. So replace the s with 256, and that's equal to 16t squared. So we want to undo this. The first thing that we need to do to get t by itself is divide both sides by 16. And so take 256 and divide it by 16, and we get 16. So that's 16 equals t squared. And the way that we undo squaring something is we take the square root on both sides. So we want to take the square root on both sides of this. And so then t would be equal to the square root of 16, which is 4. And technically this is plus or minus. The reason why we would do plus or minus when we take the square root on both sides of an equation like that is because when you square 4, you get positive 16, but you also get positive 16 if you square negative 4. And so you have to consider that t could have been either one of these. Because t is time, then we only would consider the positive value. We would not consider negative time. So 4 seconds is where this happens. So again, this number that we did on our estimate is off for a couple of reasons. We had to guess where 256 was on our y-axis, and then our curve is not drawn in there exactly either. So that just leaves room for error. How long does it take the object to fall 1,296 feet? Approximately the height of a 100-story building. So again, the 1,296 is our distance, s. So that would be equal to 16t squared. And then we follow the same procedure. We're going to divide both sides by 16. And so on the right, we'll just be left with t squared. And then over here, let's do that division on our calculators. 1,296 divided by 16 gives us 81. And then we would take the square root on both sides of this to unsquare the t. And so t is equal to, and again, this is time, so we're not going to consider the negative result, only the positive one, and so this would be 9 seconds. So it'll take the object 9 seconds to fall 1,296 feet. Now we're going to look at the graph of a quadratic function, and we're going to look at it between -5 and +5. And I think that the textbook got a little bit carried away with how many values they put into here, so we're just going to do every other value. We'll do -1, 0, and 1, but we won't do +2 and -2 and +4 and -4. Sometimes they just get a little carried away on how many points you should plot. So we already had +5 in there. Let's go back up and take a look. If you've already done a calculation, there's no sense in redoing it. When t is equal to 5, we get 400. We also have done 3. That was 144. We also did 1. At 1 second, it was 16. At 0, it was 0. Now we just have these last 3 to calculate. So if t is -1, we would have y is equal to, and change this to an s just to stay consistent with what we had. I don't know what the book has. It must have y, though, I would assume. But we'll just change that to s because that's what we had before. And so replace the t with -1. We're going to get s equals 16 times -1 squared. Again, remember when you square a negative number, it is going to be positive. So -1 squared is +1, so we get 16. Then replace t with -3. We get s is equal to 16 times -3 squared. And -3 times -3 is +9, so we get 144. And what do you think we might get for -5? Well, if we square -5, we get +25, and so we're going to get the same thing as we did when we put +5 in there. So we'll get 400. So notice, when we have, when t is -1, we get +16. When t is +1, we get +16, and then the 3's match and the 5's match. And so these graphs have a particular type of symmetry. So what kind of symmetry do we notice? Y values are the same. for, we could say, x and negative x. So now let's graph this. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, so we can do every other like we did before. And so we had our point 0, 0, and then we need to go from 0 to 400, and we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. 17 tick marks there, so 400 divided by 17 is going to give me some weird number. So we'll go 25 for each. Whoops, that would be 200. So we have 0, 0, we have 1, 16, so there's 25, a little over half, and then negative was the same. And then we have 3, 144. So this would be 25, so 144 is pretty close to 150 there. See if I can get that in the right place. And then we had 5, 400. Whoops, put that in the wrong spot. Right there, and negative 5, 400. And there I have my graph labeled, and then you can connect these dots with a smooth curve. And so there's our graph. It's not perfect, but pretty close. And then verify this on our graphing calculator. So let's pull up the graphing calculator and just show that we get the same thing on that. So we already have this function in our calculator, all we need to do is change our window. And so we want our y min to be negative 5. And just don't hit the minus key here. You want to make sure that you hit the negative sign. So we want the x values to go from negative 5 to 5. The scale on that would be 0.5. X min, or the y min, we still can leave at 0. X or y max can stay at 400. And then because our y scale on our graph was 25, we can change that to what we had. And so that graph matches the graph that we drew ourselves. So we're going to skip 13 and 14, and we're going to solve some equations here next. And I think that I will stop the video here, and we will come back and solve these equations in the next video. So if you have any questions so far on this, let me know. Have a great day.